Okay. So yeah, we're very happy to have Qiyang, Colin, Lee present online today. The title of his talk is Q-learning with flow matching policies, and Qiyang Lee is a PhD student at UC Berkeley, advised by Professor Sergey Levine. His research interests include reinforcement learning and robot learning, with a focus on leveraging offline prior experience for online exploration. Before that, he was an undergraduate student at the University of Toronto, advised by Roger Grosse. And with that, thank you very much for agreeing to this talk so early in your time. And just take it away. Thank you.
Thanks first for the introduction. And today I'll be talking a little bit on how do you optimize follow policies in Q-learning. And usually I would like to give a little bit more kind of like robotic motivation since my research interest is there. So I'd like you guys to kind of like take a look at the recent progress in learning-based robot manipulation system. So we've gotten pretty far from being able to do single tasks pretty well from just a few human demonstration, like here tying shoelaces, making pizza, pouring water, like organizing chairs and everything, to all the way multitask generalize, which is basically robots that can consume a large scale of data, like still not the same level as LMs, but I got a lot of data to complete a lot of general and diverse tasks. So there have been a lot of progress. What has really made this possible? What are the main driving forces or ingredients behind this process? So there are many things that have contributed to the progress, like what I mentioned, the availability of large-scale robotic data sets and increasingly good open source pre-trained VLMs that can give you like already a pretty good starting point so that you don't need as many like doing specific data examples. And also better losses or architecture for training or fine-tuning robot-specific representation. But today I would like to focus more on the algorithmic side. And I will point out two main sort of algorithmic points that I think actually contributed to this main progress and how we can develop algorithms on top of it. Right. The first algorithmic ingredient behind success is action chunking. So action chunking refers to basically grouping a sequence of control actions as a chunk. So the model, or in this case, a policy, can predict a chunk of actions together and execute them together as well. Well, it's originally motivated from a neuroscience viewpoint. So basically grouping things together can offload cognitive burden and make prediction more efficient. Action chunking also turns out to have other benefits like smoother motion, better temporal coherency, and it can also handle partial observability better, for example, compensating for delay. And the less obvious point is that it can also model human data a little bit better because these data often break what we call like Markov assumption, which is basically saying that our decision only depends on the current observation. And this is not true in human because we do have memory and our actions are actually very temporally correlated. And having this kind of like action chunking technique really helps to bring the model the distribution a little bit better, right? But the action chunking here actually brings with kind of a larger challenge, which is that the action chunks in the prior data often exhibit much more complex and multimodal distribution, right? So this really makes kind of the previous strategy in kind of robot learning, which is mainly using Gaussian policies to model distribution, not that feasible anymore because the distribution is very multimodal. Like we can't really represent distribution well with that. So the second ingredient actually powers simultaneously this kind of like the big progress in robot learning is also that you bringing the diffusion and flow matching into the parameterizing policies or rather generated policies to parameterize these action trunking policies. So ever since this paper, I think everyone in the field has been kind of using diffusion or flow matching policy, and they have been found that the diffusion reform machine can model multimodal distribution really well. And a side effect is that it can also generalize pretty well from just a couple of demonstration. And that's something that's really great for robot learning because of kind of the sparse data, like collecting data is expensive, which I'll explain a little bit more. But this has been kind of the gold standard for kind of robot learning, especially in the imitation line since. Okay, so let's take a look at how a standard recipe for training robot manipulation policy might look like. So we have a large scale prior experience. We're going to collect these data from, let's say, human teleoperation on different tasks. And we're going to do imitation learning, which is basically saying that I want to take the trajectory data and look at the observation. I want to clone the action chunk that happens right after the observation, right? And this pre-trained action chunking diffusion policy can already do really, really well on a lot of tasks, but it still kind of struggles to get to kind of like the 100% or like getting from 90% to 100%. So why is that the case, right? And partially I will try to argue here, as you probably already kind of know, because my background is that we really need reinforcement learning for this. It's because if we want to collect a lot of data, like LLMs, the internet scale data, we need a lot of human teleoperation, or we need a lot of data that's very costly to collect. So, and in order for the policy to go from 90% to 100%, especially important in robotics, because we want the robot to be reliable and robust, we really need a lot of like counterfactuals, and that's not easy to get if we are only collecting imitation data. And so, right, I'm trying to argue that we need reinforcement learning in this problem setting to really scale up data collection. And many of you probably familiar with this, but I just want to go over kind of the typical reinforcement learning framework that consists of following modules. First, we have a robot policy that's interacting with a physical world via actions and receives observation feedback as experience. And the experiences typically look like trajectories, which is basically kind of the alternating observation, action, and the next observation, next action, and so on and so forth. And then the agent uses this online experience to make an update so that it can do better at the task of interest. And a particular algorithm in this whole reinforcement learning framework I would like to focus on for today's talk is Q-learning. How Q-learning works is that we're going to sample kind of the transition from the data or the experience I just talked about, a bunch of trajectories. And we want to sort of optimize or estimate a Q value, which is nothing but a value function that judges how good an action is if at the particular state. So this might look a little bit complicated, but always saying is like, what will be the cumulative future reward that we're going to get if we are at the current state, taking this action and following the policy afterwards. And how Q-learning works is basically kind of like optimizing policy using this Q quantity. So it consists of two steps. You can sort of break it down in policy evaluation and policy improvement. The first step is called kind of the Bellman backup step, which is basically saying that I can use dynamic programming or approximately dynamic programming to figure out that what my Q value is based on what the Q value is for future states and actions. And if we run this to convergence, we'll get a value function that can evaluate how good my policy is under any state and actions. Right, so yeah, what is the value of my current policy? And the second step, which kind of like it's close to kind of the policy improvement step, which is basically saying that I want to optimize my policy to maximize the estimated Q value. So you kind of like notice that the Q value here is not the optimal one, which means that it's like kind of the Q value of the previous policy. So if we iteratively do these two steps, we're eventually going to converge to the optimal policy that can achieve the highest reward in the environment. And the nice thing about Q-learning algorithm is that the transition, which is the pair top tuple of state action and next state, can be all policy, right? So they don't need to necessarily come from on policy example that's collected by your current policy. They can also come from a large scale of prior experience, which is particularly suitable in many of the real world applications where we have a lot of prior experience of related tasks, but not necessarily directly applicable to the current task of interest. And in practice, how we optimize it, it's turning everything into neural nets. So Q function is a neural net that parameterizes the value from state and action, and the policy as well. Usually, how it works is that we're trying to minimize the what we call the Bellman error, which is turning the Bellman backup in the previous slides into a square loss function. And the actor loss is usually pretty simple as well. We're basically trying to maximize the Q function under the current policy. And something that people usually do, this is pretty important here, is that the policy is often Gaussian in a lot of continuous action space RL. Right, which means that your distribution or the action is parameterized by the mean and the standard deviation. And this is particularly good because now we can parameterize our actor loss using this. We can like optimize our actor loss using reparameterization gradient, which allows us to really utilize the gradient of the Q function to maximize the value of the policy. Right. So this framework has been also extended to include prior experience because Q-learning is naturally compatible with all policy transitions, as I mentioned previously. And there have been many RL methods that can effectively leverage prior experience, and I happen to also contribute to some of the progress in this direction. So going back to this slide, all we needed to do, in a lot of cases, is that instead of just sampling from the online experience, we're also going to sample from the offline or the prior experience as well. And oftentimes what we find to be pretty useful, especially in the offline pre-training phase, is to have a behavior constraint term, which is basically saying that I want to maximize my Q value, but not to go too far from the behavior distribution I'm already familiar with. And this is particularly useful when we don't have a lot of online samples and we want that for online correction, because otherwise you can go very out of distribution very quickly. And that's performance. Right. Okay, so okay, this is probably the last motivation slide I promise, but just trying to kind of get across this problem is pretty important. There are certain unique challenges that I would like to kind of mention in decision making. I guess I will start with kind of like how imitation usually does things. So usually in imitation learning, we need to capture some distribution that's often static. We have a pre-trained data set that's there. We want to just do imitation on it. And I guess in a lot of image generation case, we also have some reward function that might not change that often when you're trying to fit a model to it. So we can steer our base distribution according to some reward function, and then maybe we don't just need to deploy once, right? But in sort of online learning or online Q learning, these things are often not the case, right? So the base distribution or like kind of the behavior distribution can constantly changing because we want it to online adaptively improve, autonomously improve continuously. And the credit function, the equivalent of the reward function, which is the Q function, is also constantly changing because we're keep trying to figure out what is the best value given the current policy. And the policy is improving over time. And this also requires, as a result, also requires constantly deploying and need to be adaptive with respect to the online data fast. Otherwise, we can make a lot of progress if we can make the policy really adaptive to the online data as well. So the kind of the constraint in this decision-making land is that the Q-learning needs efficient policy optimizers to work well, especially in continuous action control. Efficient Q-learning algorithms usually use a reparameterizing gradient, for example, in DGPG, a stack. You might know these algorithms for policy optimization. By using reparameterization gradient, effectively allows the algorithm to use a gradient of the Q function, which is vector action, effectively. But previously, this was only found to be very easy to do in simpler more policy classes Gaussian policies. So the question that I'm trying to answer here in this talk is like, what can we do if these policies are not just simple policies? What if they're more complex policy, like full policy? Because clearly that's the thing that we need to use to scaling up the robot learning to more complex prior distributions. So in this talk, I'm going to present two projects, which focus on optimizing flow matching policies in Q-learning. And I'll start with the first one. So okay, I guess like please also let me know if you have any question, and I'm happy to answer any as well. But you can stop me anytime. But we can also leave it to the end if there's a question in the end. Okay, so to give a little bit of just cover ground, to give a little bit of background on the flow models. Basically, the core idea of flow model is to find a bunch of path or velocity field that transform the probability mass from one distribution to another. And the first distribution is usually a noise distribution that's easy to sample from, like a Gaussian distribution. And the second distribution is a data distribution that we like to model. And these paths often be mathematically described as ordinary differential equation, where the time derivative of each particle from the source is parameterized by the function of v. And just to be clear that the delta t here is not the environment steps in the kind of the typical RL framework. This is more the time step that's representing where some particles are in this whole kind of like denoising process. So now if we integrate this velocity field from 0 to 1, we can obtain a flow that transforms the noise distribution to our target distribution. And for training this model, we can use the standard flow matching loss, which is basically saying that we want to sample a pair of noise and prior, and we want to optimize the velocity field along the straight path towards the direction that points from the noise to the prior. And we can show that at the optimal, this will converge exactly to a unique solution under some regularity assumption that transform from the noise distribution to the target data distribution. Right. There are many strategies to sampling, but here I'm just showing one of the easiest way to sample, because essentially what we're trying to do is to solve an ODE, sample a noise, and then solve an ODE from that point. And here I'm just showing the Euler's method. And okay, let's get to the interesting part right now. So let's see how like a flow model interacts with the typically RL objective. So this is kind of like similar to the previous slides that I've shown how the objective works, but I've removed all the state just to keep the math a little bit clean. So you notice that Q doesn't have S in it anymore. And it's just like kind of just notation convenience. So what we're trying to do, this is open mirror. The value, the first term is how we're trying to maximize the value, right? By optimizing my policy. And the second term, previously we want to bring a behavior constraint in the log probability by maximizing log probability of the distribution. And here the equivalent way that we could do that is to basically minimizing the flow matching loss, which is basically saying that I want the flow policy to be as close as to the prior distribution as possible as well. Right. So, but here's a little bit problem. The first term is actually kind of difficult, right? If you do it naively. So I would like to explain what I meant by that. So if we think about the whole flow or multi-step diffusion process, it's essentially a multi-step like computational graph that we can do derivative with respect to, right? And we know that in reinforcement learning example, efficient reinforcement learning requires you to use the gradient of the Q function to get good optimization of the policy, right? So the simplest thing that one can do, or kind of the first naive thing one can do, is to actually directly backprog through this whole flow policy or the denoising steps, because we want to utilize the gradient of the Q function, and we want to use the gradient to optimize the velocity field at the intermediate steps. For this, it turns out that this can be quite unstable. Perhaps for the same reason that backpropagating through a recurrent neural network can be stable, backpropagating through a multi-step flow model can also cause the gradient to blow up over time in practice. So how can we address this issue? How can we still leverage the expressive multi-step flow model while not suffering from this unstable backpropagation issues? And the solution that we come up with is pretty simple and perhaps a little bit too simple. And the observation is that we can actually kind of distill this whole multi-step flow model into a single-step model. And if we do backpropagation through that model, it's no longer stable. It's no longer unstable, right? So what we could do is we run the multi-step flow model, and we take that, we generate a paired data sample, which is in the form of noise sample and the generated data sample, and then we train a neural network to directly approximate the map using this paired data sample. Now with this distilled neural network, we can backpropagate through it to maximize the value function without suffering from the unstable optimization issues.
So
Right,
what
so
you're training, sorry, so this by this mu theta would be like a distill model or a flow map or something like that, right?
Yeah, it will be a flow map, yeah. Exactly.
But it's you only train it for the purpose of being able to compute gradients efficiently, not because you want to use it eventually, or like.
So in this work we use it eventually, which
Okay.
yeah, which is something that we found to be kind of sufficient in this case.
Okay, sorry.
Yeah, good question. Yeah. So right, so just going back to the loss function, the first part of the loss is we want to do the same flow matching objective to have a policy that can provide us good training pairs that maps from the noise to the actions, right? And the second part, which is our actor loss right now, it's basically saying that, okay, we want this one-step actor to follow as closely to this behavior flow map as possible while simultaneously maximizing Q function, right? So this kind of like satisfies two things. We're still trying to mimic this very expressive distribution, while at the same time effectively doing backpropagation through this Q value to optimize our policy. So yeah, the main point is that this is easy now, and there's no unstable backpropagation to time. And how does it work? Let me first motivate like a little bit of kind of like the experiment setup, just to make sure you guys understand what domain that we're trying to operate in. So, and to kind of iterate our algorithms with diffusion flow policy, we really need a large core, like an offline data set that is like complex and diverse, so that this is kind of like closer to the real world where how the robot data set has been like. We use this benchmark called the OG bench, which is developed by my colleague Sohong, where it features kind of like a UR arm, has a lot of very diverse manipulation tasks, including kind of like stacking, rearranging cubes, and also there are some other tasks with diverse scenes where you can kind of like pull the drawer and stuff like that. And why this benchmark is like very fast to iterate on. And as I mentioned, it has offline data that is somewhat diverse, and more importantly, it's like more human-like. It has the data that kind of like do pick and place from random object to random location, which is does not have this Markov property, right? Because it's kind of like committing to a task and just doing it one by one. So that's like a really nice place for us to study, especially the recipe that's been working so well and in practice, which is action chunking, where it exhibits like a complex multimodal distribution in the action space. Right. So for the results I'm going to talk about, I'm going to kind of like mention both the results without the action chunking and with the action chunking. And the action chunking is like what we mainly focus on here as well. So how well does it do? Let's take some results here. And the graph here shows two distinct phases. The first phase is the offline pre-training phase, where you optimize the RL objective along with the behavior constraint so that it can still stay stable and have good performance. This is purely on the offline data without any online interaction. So that's the gray area on the left for each of the plot. And the second part, which is the white area, is for online fine-tuning. In that phase, what we do is that we're rolling out the best policy we got from the pre-trained phase to collect online data. And then we continuously fine-tune the policy using both the online experience and offline data to become better and better at the task. So the baseline I'm comparing here with are the previous kind of like the best online methods that also incorporate offline prior data. So what it does is that it kind of combines the offline and online data together and run very sample efficient RL algorithm on top of it. So RLPD is such algorithm that does so. And I'm also, because I focusing on kind of the action chunking setting, also comparing with the baseline, where if we add action chunking to this online sample efficient algorithm, and we saw that actually in a lot of tasks, in this kind of struggle a little bit, as kind of I motivated earlier, this sample efficient algorithm is using Gaussian policy, and doing action chunking can actually hurt a little bit. So let's see how well FQL or the distillation technique does on its own in the original action space. It performs reasonably well offline, but sometimes online it can still perform slightly worse than previous best online method. But the story completely changes if we actually take it into the action chunking space. So it works much, much better on some of the tasks. And on some of the more challenging tasks, like the cube quadruple, it's the only method that can succeed despite all the other methods completely fails in the online phase. Right. So this really highlights that having a flow diffusion policy in the action chunking space is really, really good. And our algorithm is very efficient to optimize the policy to maximize the Q value so that it can make a lot of meaningful progress online. Right. So at that point, I was pretty happy with how this algorithm turned out. We call our algorithm FQL because we're doing flow policy and in a Q-learning context. And I'm happy with how well it's synergized with action chunking because this sort of suggests it could be potentially deployed in the real robot. But this algorithm actually has a drawback as something that Grosse was kind of pointing out. He sort of relies on distillating a multi-step flow model into a one-step model, which obviously can sacrifice expressivity, right? And in principle, we can make the one-step model larger to compensate for loss in expressivity. But in practice, we found that even when the one-step model is much, much larger, the multi-step flow model can still generalize better and it can work better with a few data samples. So that's kind of like the practical experience on the real robot. And what are the alternatives that we can use? Oh, sorry, I just forgot to mention that these results are obtained with a chunk size of 5, except the FQL and RLPD that doesn't use any action chunk. Right. Okay. Right. So I guess I already covered this, but okay. So is there a way to avoid unstable backprop but still leverage the Q gradient? And here, trying to argue that the solution that we found to work well is adjoint matching. And that goes to the second part of the talk. I guess I'll pause here for any question. If you have any.
Yeah, I have a question.
Yeah.
So if you go back to an earlier slide where you had the loss
Yeah.
with the expectation of Q, A, and then the flow matching.
This one?
Yeah. Yes. So my question was, here when you sample A1, do you sample it on policy, off policy, or does this formula hold for both kinds of sampling?
Yeah, so is it for the first loss or the second
Oh,
one?
I'm asking about this both
Okay.
expectations.
So the first expectation, you need to sample A1 from mu because you need to optimize the policy
Okay.
with
Yeah,
respect to the
makes
Q
sense.
function. Right. For the second part, the
Right.
A1 is generated from the flow policy. Right. So that is like integrating from the the one
Oh, I
on the
see.
right. Yeah. So it's you're imitating what the behavior flow model would produce by minimizing the loss,
But
MSE loss.
A1 is still produced by your own model.
A1 is your own model.
In
Yeah. So the behavior constraint part. You're talking about the behavior constraint
yes,
loss,
yes,
right?
yes. So
Yeah.
it's not like you're taking it off policy. You still have A1 on policy, and you just try
Right.
to like enforce consistency in a way.
Yeah. So here's a little bit of differentiation here. The behavior policy is effectively cloning the data, right? So you can think of it as like kind of like a generated version of the data itself. So you can think about that as like all policy, right? Because technically mu is the only on-policy thing that we're rolling out in the environment, right?
Right.
Yeah.
So it's a non-policy. So right.
the only
So
first
this
part is
the
on policy. The second part
the
I would
second part
still
is completely
classify
off
as on.
policy.
Yeah.
I see. Thanks. Thank you.
Okay, cool. All right. I will talk about the second project that I did with adjoint matching. So I guess a little bit of background of how adjoint matching works. And it's a technique that's developed by Grosse and all of great folks in the field. And essentially, it tries to kind of tackle this constraint optimization problem that I briefly mentioned earlier, where the idea is to kind of maximize a flow model or a fine-tuned flow model with respect to certain value function or reward model. In this case, I kind of translate the whole formulation into this action and value space and the policy space, just to keep the notation consistent. And just to make a little bit of connection as a side note, the previous algorithm that I just presented, the flow Q-learning algorithm, approximately imposes a slightly different constraint, where we can write it as sort of watch assigned to distance between the policy and the behavior policy. Right. Okay. Cool. So how does adjoint matching work? Let's start from the center flow flow matching ODE. And we're going to add noises to the flow matching ODE. And this can be done by adding some noise and then pulling the samples back by hill climbing on the score of the gradient of the score at intermediate denoising samples. Right, so this is nice because it sort of gives us a way to arbitrarily denoise our samples so that they can be stochastic and helps us to optimize the sort of KL objective. And from the full matching literature, if we know that the H0, the full Gaussian distribution, we can also kind of like relate the velocity field and the score, the gradient of the score very directly. Assume kind of like a standard denoising schedule, which is kind of like a linear schedule that goes from the noise to the data samples. And this will allows us to kind of like rewrite the whole equation using only the velocity field, where again, the sigma here is how much noise we're adding at each individual time step throughout this process. And intuitively, this is basically saying that this is kind of like the motivated mission, that we can add arbitrary noises to turn this ODE into an SDE while preserving the marginal probability distribution, as long as we pull back the sample with a stronger velocity field. And what adjoint matching does with this is that it uses a particular noise schedule that satisfies what they call a memoryless property, which basically says that the generated action sample or generated sample is independent of the noise, right? And this allows us to really simplify or connect the objective directly to the KL constraint optimization problem, right? So now the nice thing here is that we're basically saying now we just need to minimize the MSE error between the fine-tuned velocity field and some behavioral velocity field that we're pre-trained, and maximizing the value function under the generated samples, and that should give us the optimal KL constraint policy here. But the problem with this formulation still is that this sort of like basic simulation is that the optimizing this still requires backpropagation through time, which is not ideal because I mentioned this could be unstable. And we can write out the equivalent backpropagation gradient via a backward OD. And this is also in the adjoint matching paper, where you can kind of like break it up into where the KL gradient is and how the backpropagation gradient through the velocity field is as well. You can see that they're kind of depending, because of the backpropagation through time, they're kind of depending on the fine-tuned velocity field, which is kind of like on policy. And that's can lead to instability if your fine-tuned velocity field is like ill condition, right? And actually matching argue that can actually avoid this largely. And the way that they do it is pretty smart. So basically, they're saying that we can actually convert this gradient, or they call it adjoint ODE, into something that's called adjoint, which essentially gives you the same optimal, but it removes all the terms that is related to the fine-tuned velocity field, right? So what is nice? Okay, yeah. So the term that's in the adjoint matching linear adjoint objective, or the ODE, is independent of the fine-tuned velocity field. Right. So the nice thing about this particular objective is that it uses as long as the behavior velocity field is well conditioned, the gradient computation will be stable, right? And this is something that's also found in our experiments, where I found that if we use adjoint matching objective, it tends to lead to better performance compared to the basic version, right? So this is kind of like pretty nice. And I actually found that this particular adjoint matching technique is one of the first methods that worked really well on some of the hardest benchmark. So which I will show the results. Right, and just a little bit intuition, additional intuition here is that how adjoint matching works is that it uses the behavior velocity field and the gradient through that to estimate the gradient during backpropagation instead of actually needing to use the fine-tuned velocity field. And that is where kind of the different stability comes from. Right, okay, so how does it work? And I did quite a bit of work to try to properly evaluate this method against all possible flow plus RL method that I could think of. And it seems to work pretty well across the board. So this is kind of like in the offline RL setting where we are given a bunch of offline data and we want to train policy to do well on the data on the task where we relabel the data with a different reward function. And this is across 20 local motion tasks and 30 manipulation tasks in this OG bench benchmark. And I found that the virtual matching can consistently outperform the other methods, which includes some classifier guidance method, RL in the latent space, our previous distillation method, and also the basic adjoint matching, which doesn't use the linear adjoint objective. It also outperforms other like residual RL type of methods. I also found that adjoint matching standardized pretty well with residual RL, which is basically saying that I want to edit or change the fine-tune policy by a little bit more by another policy that kind of like only locally change the actions. Right, so there are two variants that I explored. The first variant is that I'm adding a Gaussian edit policy, which is basically saying that I first take the output from the adjoint matching fine-tune policy, and then we're going to edit by a certain magnitude that cannot be larger than, let's say, 0.2 in the absolute magnitude, action magnitude. And the second variant that I explore is to actually combine the FQL with CAM. I found that that can also work reasonably well as well. And how it works is that instead of using the behavior policy as the paired data sampler, we're going to use the fine-tuned policy. So in this case, rather than the out policy, this will be more on policy version for that, where the CAM fine-tune policy is used to generate the data sample for the FQL distillation to work.
I see. So this would be the on policy version of the flow matching.
Yeah, that's right.
Distillation loss.
Yeah, that's right. Right. So I previously showed that how it works in offline setting. How well does it work in the kind of the online fine-tuning setting? So you notice that all the graphs a lot of the curves doesn't start from zero. This is because they were all offline pre-trained in the first place. I'm just like removing the offline part just for clarity in presentation. But the results are in the main paper for the full curves. And I'm focusing in particular on the action chunking setting because that's something that's like pretty important in a real robot system. And they're all adapted. I adapted all the prior methods, even though they were not designed for action chunking, to use action chunking and tune the hyperparameter to the best of my to the best I could. And it turned out that well, on some of the tasks, the performance seemed to be pretty similar on, let's say, the cube task, double task, and the quadruple task. But on the triple task, CAM is still able to do much, much better in terms of online sample efficiency. So it suggests that using the gradient while not sacrificing expressivity seems to be a really nice recipe that leads to good empirical results. So just to recall here, FQL uses distillation, but it only has the one-step policy. And the RLPD and the readbacks are the Gaussian baselines here, which doesn't work well on some of the very hard tasks. Okay, quick takeaway before I go to future work is that we can translate the success of generated policies from imitation learning to reinforcement learning. But it requires good algorithms to optimize them with respect to value function while not suffering from unstable optimization problem. So I presented two algorithms. The first algorithm IPL, which uses one-step distillation that avoids unstable backprop, but it can sometimes suffer from expressivity loss from distillation. The second algorithm improves upon it, which is gradient-based and avoids unstable backprop, with no distillation, and it seems to yield the best results for Q learning on this offline to online setting with action trunking policy. Right. One downside with oh, do you have any question?
Oh no, sorry.
Oh, okay. One downside I will still mention with CAM is that I can still observe instability sometimes in practice. And I suspect that this is still because it's doing some sort of a backpropagation still, where when the behavior velocity field is ill-conditioned, it can still lead to instability and the policy optimization. So there's a little bit trade-off. Like CAM is great, but sometimes it can be a little bit unstable. FTL is really stable, but sometimes it suffers from this expressivity loss problem. So what is next? Oh yeah.
Sorry, excuse me. On this instability point, I have a question on: do you use guidance for this diffusion classifier free guidance? Sorry, for this diffusion policies?
No, I don't use.
Oh, so you run the generations without any kind of guidance?
No, yeah.
Okay, cool. Yeah, nothing else.
Okay, so what is next? Okay, so what is next? And how to basically the question I'm interested in answering is that how can we leverage both the Q gradient and the Q value at the same time, right? So this is like something that I keep seeing in practice is that whenever the gradient of the Q value is not great, all the gradient-based methods seem to suffer a little and suffer from instability problem. And if we have poor gradient, Q gradient, the best thing that we could do seems to be using some sort of like global optimizer or sampling-based method. We sample a bunch of them and we pick the one sample that achieves the best Q value. And when we have good Q gradient, we seem to want to utilize the gradient to do gradient-based optimization in the action space, right? And having designed an algorithm that can do both of them or finding a good trade-off between them will be pretty nice. So far, most of my work has been focusing on kind of how we use the gradient-based optimizer, but perhaps making more progress on how do we have more sampling-based approach into RL and Q learning will be make more progress there. And the second thing that I'm interested in tackling is that so far our algorithms are still not very sample efficient. As in my graph, I've shown that it's showing here the online phase might take up to kind of like 5 to 6 hours to just make a little bit of progress in the plot here, like to learn something reasonable. And that is 5 to 6 hours of real robot time. And it will be very, very good if we can bring it down all the way to maybe like 30 minutes to an hour, because robot times are very expensive and we can scale much better if we can make the RL algorithms more efficient. Okay, so that's all I have for now. And I would like to thank my collaborators on all the projects, Paul and Sohong, and my advisor, Sergey. And I'm happy to take any questions from here. Yeah.
Yeah, if someone online has questions, please go ahead.
Oh.
Yeah, great talk, Colin.
Thanks.
So I have a very maybe brief question. So in case I missed it, I think you are learning two networks, right? So one is for the actor and the one for the critic. Like one you called mu theta and the other called Q. Like the Q function.
Yeah, that's right.
But there is some consistency between the two, right? So just kind of like your Q function tells you your optimal what's your optimal policy. Yeah, why don't you use a consistency between the two?
So what do you mean exactly by the consistency again?
Oh, it's like yeah, I mean, I'm mostly thinking about continuous time because Curtis and I work with mostly continuous time, where you have value function. Like the gradient of value function is your optimum policy. And so you can basically parameterize your the value function or the Q function already gives you pi in optimality, like a pi star.
Yeah.
So yeah, I
Okay.
mean, it seems the issue you mentioned on the either use the gradient of the Q or the Q function can be somehow addressed by correlating the two. Does it make sense?
Right. Yeah. So yeah, good question. So first of all, the Q function here is probably not optimal in the beginning and will never be close to optimal, I guess. We're trying to optimize it to be optimal, but the Q value we can like try to learn would still be kind of like on policy Q function. So it will be the Q function that is
I see.
evaluated using some policy, right? And so it is really an iterative dance between the Q value and the policy because we're trying to say that, okay, based on our current Q function will be a better policy, right? And this better policy will lead to a better Q function as a result, and so on and so forth. Because you still need to somehow distill that information from the dynamics, right? It's a multi-step dynamics, right? So you need to figure out what the change in my policy or the Q function in the future will propagate to the earlier time step, right? So that process needs to still happen somehow. But you're right that
have people tried using the theta and the psi at the same network, for example?
Yeah, so yeah, that's a great question. So you could, in principle, or I'm going to say, you could, in principle, parameterizing the actor directly using, let's say, the gradient of the critic in a way. I think in general, I haven't had a lot of success with it. I think in general, it might just seem to be that parameterizing the gradient of the value function might be a little bit hard to work with directly. And the ones that seem to be most successful right now is to have some sort of like intermediate thing where you could have a diffusion policy or a flow policy where you matches your step, denoising step to the gradient.
I see.
Like kind of like an intermediate, like a compromise step. But I agree it would be really cool if we can come up with an algorithm that can do this directly in RL, like the robot learning setting. But yeah, like I've tried myself a little bit with this, but it didn't.
Maybe we can chat a bit more on it with cars as well, because we've been having some success like in the continuous time domain.
Oh, that's pretty cool. Yeah.
Well, I'm not sure, but it works quite well in our case, so we can talk.
Wait, what's the task?
Sorry, what's the cost? What do you mean? What's the cost? Sorry.
Task.
Sorry, what are task?
Oh, the task is like on rare event estimation. So basically you can consider the robot navigation, but you have a base process which is a long-driven dynamics, and you have very high energy barrier that you need to cross. Which means under your base reference process is very rare. It's called rare events. So you got to navigate the right way to cross the barrier. It's kind of like a robot navigation. But you have a lot of zigzag in between. So if you just do random exploration, it will just exponential hard to solve.
Right. So it's kind of like this continued like decision making process, or
continuous space and continuous time.
Okay, cool. Yeah, I would love to chat more. Sounds pretty interesting.
Yeah, thanks. Thanks for talking.
We can set up a meeting after.
Okay, maybe Michael, if you want to unmute yourself.
Oh yeah, can you guys hear me?
Yeah.
Is there? Okay, great. Yeah, I don't know. Just to add to the previous discussion, I don't know. My impression is that sort of, even if you have a Q function that's perfect, optimizing the action space is still like an arbitrarily hard problem for most robotics tasks. Like, there's sort of, even if you had access to it, you'd still have to do something that looks kind of like diffusion just in order to like optimize and find the best action.
Yeah. And I guess like if you have a perfect Q function, you could do something like Langevin dynamics too. If the gradient is okay. But
Oh yeah, I guess
yeah.
also going back to the same comment and to what Michael just said. Yes, I think we were thinking with UNC in a case where we don't do action chunking. So we only yeah, so we don't model like say 5 actions at a time, but it's just the current one.
Yeah, I think that's fine. Yeah, I think that's like for a local motion task, it's like perfectly fine. I think I've only found like action chunking to help a lot in a manipulation, which is a lot
I see.
of like where our lab has been focusing on. Really,
Yeah.
but for local motion, I think is not that great.
Yeah, it's
perhaps.
kind of interesting because I would consider our task more like a global motion, right? It's because you have to cross the rare events. So it's kind of like you can't be just myopic, because if you just look at your local, you're just gonna stucking at the local minimum, because there's an energy barrier separating where you want to go. Well, we should okay, I guess there are a lot of nuances for this, but I guess it'd be interesting to see if there be some nice connection, because I'm not the RL guy, and thanks a lot for the background and everything in the talk. Yeah.
Yeah, I hope it was helpful. I try to motivate a little bit more.
It's very good.
Maybe. Okay. Okay. Thank you.
And okay, I have maybe one last question, which is, in when you wrote down the algorithm, you only wrote the dependency on the actions. So I was wondering if you could comment a bit on how the dependency on the states appears in the gradient. Is this hard to deal with, or is this just straightforward?
Oh wait, sorry. You mean like these kind of objective? It's only
yeah, exactly. Yeah.
Okay. So it's because like in RL state, if we abstract away the critic learning part, only focus on the actor learning part, it's basically just saying what we want to do, condition on the state, with respect to these things. So that's why like the objective is like agnostic to say. State is just like conditional variable, basically.
Right.
In our case. Yeah.
Okay, got it.
Obviously, you can do something fancy on like classifier guidance, but I don't think we tried that we have tried that before. Yeah, but that's always a possibility. Yeah.
Yeah, I guess everything is already encoded in the function Q. So like because I would assume like another way to take this well, I mean, backpropping through ODEs like could be also to have an estimate, like a Monte Carlo estimate of Q, and then you could also backprop through that. But I'm guessing that's really not. Yeah, I mean that you're doing like an actor critic method precisely to avoid that kind of issue.
Yeah.
Otherwise, it would just be an actor. So yeah,
it would just be high variance. Basically.
Yes, it would be horrible variance.
But in some cases it's like nice if the variance is not.
Yeah, I mean it is like for LMRL, like that's what people do. Right? It works.
It's okay. Yeah.
Yeah. Okay, so I think that's all. But yeah, happy to sync more offline.
Yeah. Thanks for inviting me. It's very fun.
Okay, so I guess let's thank again.
Yeah. Thanks everyone for coming.
Thank you very much. Great talk.
Thanks. Bye.
Thanks. Bye.